So my name is Taylor McClain. I'm the Director of Engineering for GridSME's Engineering and Interconnection group. Welcome back to everybody who was on the session this morning, and welcome to everybody who didn't join us this morning. Just a little overview of what we'll be covering now. This morning was focused on how to kind of prepare for the interconnection request package. And this discussion now is going to be focused on how to actually prepare that interconnection request package and kind of the details that are important going into that for folks who are developers and who are building these projects but are not doing the work in-house, kind of a little bit of hints and tips on how to work with your consultant the best, just how to make sure that everything goes smoothly. I will mention, if you were on the discussion this morning, there are going to be some topics that we go into again. There may be a little bit of covering items again, but I think it's from a different perspective and kind of focuses on things a little differently. So hopefully it's not too much of a repeat for folks, but with that, I think we'll go ahead and dig into building a successful interconnection request package. So the first thing to kind of go through is, assuming that you're working with a consultant, or even if you're just working with your in-house group, there's kind of a range of what you're going to need to provide. And anywhere in that range is fine, but there needs to be some communication made about what things are being provided and what is already decided in the design. Basically, if you have the least amount of information, you're going to at least need to provide the megawatts that you want to interconnect at the POI. You will need to provide the location of the POI name, voltage level, all of that. And then you'll need to provide a KMZ with a site boundary for your specific location. If you want to, you can take it all the way to, having a full design prepared, detailed site plans, inverter counts figured out, your inverter selection, your gen-tie route. For us here at GridSME, we'll take anything that you can provide. When what we've learned from our experience is when you are providing this type of information, it's helpful to make sure that you have it pinned down as early as possible in the process, and also be open to potentially changing some of those items dependent upon the utility requirements. One of the things that we notice a lot is when a client does come to us with an inverter count, there are often times when the power factor requirements, the losses, things like that weren't quite vetted out. And so we'll run a power flow and we'll say, hey, we need to add another inverter in order for this to meet all of the requirements. And so if you are providing an inverter count specifically, just be kind of prepared to work with your consultant and make sure that, you have the correct inverter count. And the other option, if you have an inverter count that you need to stick with, if you don't meet those requirements for a certain megawatt amount, you could also reduce your megawatts. So there's options if you're pretty set on your inverter count, but just something to keep an eye out for. So the bulk of this presentation is going to be kind of going over the different design components of a facility and how those relate to the interconnection request package, how to kind of select items and how to work with your consultant on this. One thing to kind of note ahead of time is that, we do understand that the final design is going to likely be very different than the initial design. With these long-term projects that span years and years, we know going into it that the inverter you select when you submit the interconnection request package is likely not going to be the same. We know that what you can procure at the time when the project is ready to be constructed is going to differ from what is available today. But with that in mind, within reason, if you can try and have the design as close as possible to what you're expecting, it will certainly help you out a lot with, not having to submit so many MMAs down the line and things like that. So, with that in mind, if you do have specifics that you've used on projects in the past, or things that you are likely to be set in stone for your project, it is good to let the consultant know. In our case, we estimate a lot of values with the typical values we understand are good approximates. But if you have some that are more specific to your projects, definitely share those with your consultant ahead of time, knowing that an MMA at some point is going to be inevitable. All right. So we this morning we definitely talked a bit about AC coupled versus DC coupled and kind of how to prepare with your design for that. Now we're going to kind of talk about where that comes into play when you're actually preparing your package. So if you've decided on going with the DC coupled, something that we've seen often is folks will spec a solar inverter, basically a non-bidirectional inverter for their DC coupled project. It's very typical, but every once in a while it gets lost in translation that the developer is going to want to charge from the grid at some point. And when we have these non-bidirectional inverters, that does become a problem. So one of the things to think about is definitely, looking into whether you need a bidirectional inverter or not, because that could come into play even with your DC coupled design. Something else that we touched on a bit this morning was about one of the potential downsides to the BESS is that when you physically construct this, more than likely, if it's a large solar facility, you're going to be spreading out the BESS along with every single inverter out in the solar field. So that's just something to think about for the construction phase and some items that could potentially be a little bit more troublesome in the future versus with an AC coupled where you can locate your BESS pretty centrally to your interconnection facilities and have a smaller collector system and some pluses on that side. So definitely something to think about if you're on the fence of DC coupled versus AC coupled. So another thing as well, charging from solar only, we do see that pretty typically when a DC coupled facility is selected. It will reduce how you are able to operate your facility. Obviously, you won't be able to charge from the grid. You'll be limited to whatever capability you're getting from your solar. And when you do need to charge off your solar, obviously at that point, your solar is not going to be producing to the grid its maximum amount. So if you're looking for the lowest impact design, certainly going with no grid charge is going to be beneficial. You won't get studied as a load, and it is just a smoother interconnect. But what you're giving up is some of that functionality of the BESS and solar working together. Another item that is not as important at these very early stages, but if you want to try and get that design as close as possible, like we talked about before, it's good to start considering the DC inputs on your inverter. If you're doing a DC coupled facility, you may end up with more DC inputs than you would typically end up with for solar only or battery only. So you want to just be taking a look at what you're speccing and what the options are for that, and make sure that the design on your DC side, or what you expect it to be, is going to work out with the inverters that you have selected. Once again, not terribly important in these early stages, but it does not hurt to start thinking about it. So DC coupled, this is basically your overall DC coupled design. It's going to look more like just a single generator. This is the equivalent look at your facility. This is basically what your power flow model is going to look like. And when you have DC coupled, it ultimately looks like just a single generator because you just have a single type of inverter on one side, and a single set of pad mounts because those are going to be shared, and so on all the way down. However, when you go with the AC coupled design, basically what you're doing is you're now connecting a second type of generator, a new battery storage inverter, and everything is ultimately going to get connected at the medium voltage bus of the main power transformer, often called the collector station, because it collects all the feeders. And this is what that's going to look like, where you will ultimately, at least from a modeling perspective, you will reflect two generators, and everything is connected at that medium voltage bus. When you're charging the BESS, you are going to have, or charging the BESS from the solar, you are going to see the losses through the solar collector as well as the battery collector for the AC coupled. So with AC coupled, as I mentioned a little bit ago, the BESS facility can now be located close to your main power transformer, close to all your interconnection facilities. And this can be really helpful because it reduces the collector system involved for the battery storage system and reduces the losses. Something to note for the AC coupled, we asked pretty frequently is if you can pair different inverter manufacturers. We have not seen this be a problem. You can certainly mix and match your inverter manufacturers. I think there are likely some benefits to the procurement side if you're keeping things the same, but we see plenty of folks speccing different inverters on an AC coupled design, and we see no problems with that. So definitely something that you can do if you have a battery energy storage inverter of choice that you like, but want to stick with the solar inverter you normally use, that'll be totally fine. As mentioned, the collector system losses for charging from solar, and then kind of the final potential downside to having the AC coupled. I will note that in general, inverter-based resources have a much lower short circuit duty contribution than something such as conventional gen. Historically, there aren't too many issues with short circuit duty contribution from inverter-based resources, except for areas where there is high concentrations of inverter-based resources. So this isn't quite as much of a negative, but it is something to consider if you are interconnecting to an area that is known to have circuit breakers that are already stressed pretty highly, is that you will now have two sets of inverters out there and a much higher MVA, I mean, essentially double MVA installed capacity, which will result in a higher short circuit duty contribution and could potentially lead to determining there are network upgrades needed to support that. So potentially an area where DC coupled could save you. But once again, you got to kind of compare the pros and cons of both options and see which works out best for your project. So we're going to talk a little bit about project sizing. So you kind of have a couple of different factors. These are the high level factors that really are going to bound your ability to go to a certain size. So your available land and a detailed site plan. As we mentioned this morning, definitely a good idea at this point, if you have the resources or you have the ability to go ahead and prepare a somewhat detailed site plan ahead of time, it's going to be a very helpful option because it's going to just help you understand a little bit more about the viability of your project. And one of those things being how much of any type of generation you can actually fit on your land. So this is going to create a very hard bound unless you can find additional land in the future. Whatever you can fit on your land is going to be what you can get. So knowing this ahead of time is definitely very helpful in deciding your project sizing. So the project sizing is the desired megawatts at the POI. It's the maximum amount that the utility is going to study you for. And the reactive power requirements, which we also discussed this morning, are kind of the other factor that sometimes is overlooked, where you might think, oh, I want 50 megawatts at the POI, then I need to install 50 megawatts. And between losses and your reactive power requirements, it ends up definitely being a higher value of MVA installed capacity. So these all factor into how you size your project.
Hey, Taylor,
So something.
Quick question.
Oh, yeah. Mm-hmm.
So the question is, what could be possible issues while using different inverter vendors for PV and BESS in AC coupled systems?
I have yet to see potential or to see any issues called out by the utility. I actually don't think there are really any particular issues that could be seen related to that specifically. They're so separate at that point that there's not much of an interaction. Potentially, and I won't claim to know a lot about this, but maybe certain PPC power plant controller manufacturers might only support certain types of inverters. There's potential for there to be a little bit of mix up in the crossover, but I think in general you're pretty safe to go with any inverter pair. It is certainly something that could be run to ground with an inverter manufacturer. Most folks don't have their PPC manufacturer in line in the early stages, so maybe that wouldn't be as pertinent. But so far, from a functional standpoint, I have yet to see any issues. And as well as from a utility input standpoint, we have not received any deficiencies specific to pairing up to specific inverters. So I would say in most cases, you're probably fine to go with either pair that you like.
Great, thank you.
So we're going to talk about the detailed design, the site map, and the power flow, kind of these two factors that play into each other a bit. And they end up being a little bit of a chicken and an egg scenario, because when you are working in an area such as New York ISO, where they are looking for this pretty detailed site plan in the very beginning stages, you are also in a situation where the number of inverters, the length of the collector system pieces, the length of the gen-tie, all of these factors are going to show up in your detailed site plan and then have to be replicated in your model. Now, if you prepare the detailed site plan first, you're doing this without having the exact understanding of the power flow and what the reactive power losses were, what the real power losses were, and how many inverters you truly need to get the proper design. So, but if you start with the power flow, you don't have quite the exact information you need to build your equivalent collector system, and to know some of the more specifics of that. So it's a little bit of, you need them both to get the final result. And it can be a little bit of an iterative process. So if you are required to provide detailed site plans, or if you have the detailed site plans prepared for internal uses ahead of time, our suggestion is to take that first draft of the site plans and go ahead and use that as your basis. Provide that to your consultant and say, hey, this is what we're looking at working with. Can you go ahead and run your power flow on this so that we can see how our design does on the reactive power requirements, on the losses, and our overall inverter count. The consultant can then prepare a pretty exact equivalent collector system given your detailed site plan. They can get some really nice impedance values that are close to the final design, go ahead and run that power flow, and then report back and say the inverter count was good or the inverter count wasn't. In most cases, we do find that additional inverters are needed. Sometimes it might be the case that less inverters could do the trick as well. And so at that point, it's kind of up to the developer and the consultant to work together and decide what the next step to move forward is. But at that point, you kind of have your first draft of both the site plan and the power flow model pulled together. And you'll just basically at that point update them both. I mean, starting with the site plan again, you'll update the site plan to have the correct inverter count. And then the consultant can go back, reconfigure the impedance values for the collector system, recalculate the MVA installed capacity, megawatts with the new inverter count, and then you can move forward with the project. One note is that when the detailed site plan is required by the utility, it's very often that they're going to need to see that those models and the detailed site plan line up very specifically. New York ISO being an example, they were wanting to see collector lengths for each of the feeders. So in that case, you really do need to make sure that the detailed site plan and the power flow models are being worked on very closely. This isn't much of an issue, except for what we've typically seen is that it's two different sets of folks working on either. So as long as communication is good, then typically things are fine. But it just needs to be reminded that if a change happens to one or the other, then it needs to be relayed to the other party, because these can cause deficiencies that can really hold up projects in the interconnection process. So just staying on top of that, the typical thing that happens is the detailed site plan changes, and potentially somebody isn't informed. So any changes to that detailed site plan when you're working with an ISO that is really strict on the requirements for lining things up, just be sure to be very communicative with between the two teams. So if there is no detailed site plan required, it is a little bit easier of a process. At that point, I would say allow your consultant to start with their estimated inverter count. There are techniques to estimate a collector system equivalent pretty well. It's not going to be specific, but if you're not comparing your collector system impedances to an actual detailed site plan, then the main thing you want to make sure you're doing is just approximating the impedance values high enough to make sure that you're not selling yourself short. In those cases, it is a lot easier for the consultant to just run their power flow until they figure out the optimal design. And then at that point, they will share with you like, hey, this is the inverter count that we're going for. At that time, if you do want to prepare a detailed site plan for helping with the viability of your project, then you have an exact design to go off of. So definitely a little bit easier when, or a little bit less of an iterative process when you don't have to submit the detailed site plan and when you can go ahead and just start with power flow models, understanding that they both play an important role in determining potential bounds for the inverter count. So in the spirit of talking about reactive power requirements, once again, we're going to touch on FERC Order 827. So this is kind of one of the main sides where we run into deficiencies when we're trying to cut this inverter count really close to meet the reactive power requirements. You know, for these very initial stages, it oftentimes works out best to just allow for a little bit of overbuild in the beginning, just to make sure you're not cutting anything too close, and also to allow for potential design changes. Because the last thing you want to do is build this thing exactly to the point where it can meet this reactive power requirement, and then find out later on that you now have to change your gen-tie route. It's going to be a mile longer. Now you have these additional losses. Now you have to consider adding inverters. And it's much easier in the MMA process to reduce your MVA installed capacity, reduce your short circuit duty contribution, and reduce the equipment installed at your facility than it is going to be to add additional equipment back in to increase your MVA installed capacity and to increase your short circuit duty contribution, and in some cases can actually cause problems with making that material modification deemed material. So within reason, we don't want folks to get too ahead of it and over install more than they need because of the cost of the equipment, and also because of the higher MVA installed capacity and short circuit duty contribution. But we do suggest that when it is possible, to not cut your reactive power requirement headroom too close, and maybe give yourself an additional 5 to 10 just to be on the safe side. Another thing to consider in that is the auxiliary load. This is very likely to change from when you initially start to when you finish the project. And oftentimes one of the things that isn't known too well is exactly what the reactive power of the load is going to be. So really at this stage, considering that as well, the additional headroom is going to help you make those fine-tuned changes that you need to later on in the process without running into these roadblocks where you're making changes that are now going to impact the grid more than your original project design. Because that's really the key, is starting with a design that you will only make less impactful. It will definitely make your life easier as you go through the process. So one of the things we were talking about this morning too was the 0.95 power factor requirement at the high side of the MPT. I will say at this time, we're talking specifically inverter-based resources, non-synchronous gen right now. I think this is what most folks are focused on. Certainly, if we didn't cover a topic specific to a type of generation that you are developing, we're happy to get some questions on that and provide some details. But this right now is focusing on the inverter-based resources. And so there's kind of two requirements, and sometimes it's presented a little bit confusing. It'll say 0.95 power factor at the high side of the MPT, meeting this dynamically, and basically saying that if you add a capacitor bank, it can only be as much as the losses in the system. What this is basically saying is that if you can install enough inverters to meet a 0.95 power factor at the generator terminals, you are allowed to install a capacitor bank to cover whatever else additional it takes to get that, to also get that 0.95 power factor at the high side of the MPT. So, most of the time we we recommend, and most of our clients stick with the installing of inverters to meet the reactive power requirements. It leaves plenty of room to add capacitor banks later on if you want to. And it's typically ends up being a little bit of an easier design, only for the fact that we have seen a couple of projects where the capacitor banks were causing harmonics issues, and then this resulted in them needing to remove the capacitor banks and go ahead and increase their inverter count again. In these cases, they were pretty large capacitor banks, so we aren't really expecting to see the 5 to 10, these smaller ones covering smaller amounts of losses causing too many issues. But really what it comes down to with the inverter overbuild or adding the capacitor bank is the cost of procurement. That's the big thing to consider. If you think that you can cover these additional 15 MVAR of losses, let's say, with a capacitor bank for a much cheaper cost, then maybe that makes sense for you to go ahead and do that. But if you're looking at a similar cost, then there may not be too much of a benefit to adding the capacitor bank. So I will say with that, it is definitely a case-by-case situation, and there are a lot of factors that could play into this, including ISO, PTO considerations and things as well. So on a project-by-project basis, definitely good to work with your consultant or your internal team to determine what's your preferred method for overbuilding for reactive power. So this slide, we're going to talk a little bit about the battery energy storage facilities in general. Looks like we have a question.
Yeah, that was a follow-up to, there's one question that was a follow-up to the earlier question,
Okay.
and then another new question. So the follow-up was, so electrically, harmonics, etc., won't be a problem, but PPC/SCADA have to integrate 2 separate inverter OEMs. Is that correct?
Yeah, that's correct. And that's where, like I said, I don't want to say I haven't seen that be a particular issue. And I actually can't claim to have seen a particular issue by pairing up 2 separate inverters, but I do foresee that as potentially being an issue. But I don't know. I don't work with too many different, PPC manufacturers. And typically in these early stages, we're not speccing the legitimate or the final PPC manufacturer. So I can't say that for certain, but it could be something to look out for and that you may want to look into prior to selecting these. And I think that would ultimately be a conversation with the inverter manufacturers potentially, but ultimately probably a conversation with a PPC manufacturer. And given the number of PPC manufacturers out there, there may be enough overlap that this doesn't become an issue.
Great. And then the new question is, how will IEEE 2800-2022 be relevant, and when do projects need to comply with the standard? And actually another part of that, but go with that one first.
Okay, well, I was going to say, I'm actually not super knowledgeable on that right now. I think that would probably be best as a follow-up question to this, if we can take that one down.
And actually, I think I can answer part of that for when we're going to cover the IEEE is going to be on Wednesday. We have kind of our NERC 101 session and some upcoming standards with NERC, and we will be covering some of that IEEE stuff because that is new to the projects that we're seeing. Then the second part of the question, Taylor, is we see inverter OEM offer capabilities as per IEEE 1547-2018. I'm not sure if that was a question or just a follow-up statement to the first part. Okay,
yeah, not sure either, but if it is a question, we can maybe get some clarification, and I'd be happy to see if that's something I know or if it's something that somebody else knows. Cool. Okay, so talking about BESS and storage capacity a little bit, something that we have seen recently is, typically the battery modules and inverters are a separate selection. We actually, for a lot of utilities, PTOs, ISOs, we are seeing that they aren't even requesting that you provide the details on what battery module you choose. So at that point, typically, we're just assuming some amount of megawatt hour installed capacity. But something to note is that there are some inverters that are designed modularly with the battery modules, like the Tesla inverters, and they have kind of set megawatt hour capacities that you can choose for their different inverter options. And we recently kind of ran into some some issues with the capability to find the right combination to meet specific hour duration options. So that's just something to consider if you're going with the modular battery and inverter design, is just make sure that they support the design that you want to go with. Otherwise, what you're really looking at is, as we talked about before, the DC input count. Let's say that you want to do an 8-hour or a 12-hour system, which we have started to see a little bit of those being proposed. Well, now you're going to need a lot more battery module counts behind each inverter. So at that point, you need to make sure that there are large enough battery module components with single inputs to be able to be supported by the number of DC inputs on the inverter that you're selecting. Power Electronics has a line where they have a couple of different options from 2 to 4 inputs. So, you're definitely going to want to be looking at potentially these 4 input counts if you are going to have an 8 to 12 megawatt hour system, just so that you can have the inverter that supports the capacity that you want to have installed. So just another way that you can kind of save yourself from a potential roadblock or a potential MMA down the road if you're just thinking about these things a little bit ahead of time. So another thing that we've started to see come up a little bit more now that batteries are, more of the norm, and the utilities are taking a look at these designs a bit closer now, is that the primary frequency response range is requested. And typically in these early stages, we would have maybe said, okay, 0 to 100%, because we're not really sure at this point. It really depends a lot on your battery module, on your PPC as well, on the inverters, on a number of things that aren't totally pinned down at this point in the project. But what we are finding is that some utilities are rejecting the 0 to 100% because it is a very clear estimate of what is possible. If the inverters don't and the batteries don't have the operation range baked into that 0 to 100%, then it is very likely that it's not going to be 0 to 100% and that you're actually going to have a smaller usable range. So what we're finding is that it is becoming more and more pertinent to kind of think about how much of an overbuild of your megawatt hour capacity you're going to need to support the megawatt hour that you're going to claim to be using. So basically, that's just saying that you're going to need to install more megawatt hours than you're actually going to be able to use based on this limitation. An example being, if you wanted to have a 100 megawatt hour capacity, but you have determined that you only have a functional operating range of 10 to 90%, then your usable capacity is actually going to be 80% of that 100 megawatt hours, coming in at 80 megawatt hours. So now if you want to have that 100 megawatt hour design, you're going to have to overbuild your megawatt hour capacity in order to meet that, and to meet the range that you're saying you can offer primary frequency response range in. Looked like another question on this.
Yes, we've got a question. How is this functional operating range determined?
So from what I understand, I think this is largely the battery module that's going to determine this, because what it comes down to is how you can safely operate the batteries. At least that's my understanding. I'm happy to learn a little bit more on the topic. I will admit I'm certainly not an expert in this, but from what I've seen and read up on, I think it's largely related to the battery module that you choose to limit that, so that you can, extend the lifetime of these things and operate it in the range that it's designed to operate in. So next component to go over here is the auxiliary load. So once again, this is much more specific to battery energy storage than some of the other types. Well, I mean, if we're talking solar and battery, it's much more specific to battery. So the battery energy storage design that we're typically estimating is somewhere in the 2 to 3% range. I have seen constructed facilities where this actual load is in that 2 to 3% range. So we do know that currently with the technology and with how how much HVAC is needed for these batteries, that it is realistic to specify 2 to 3%. There are some inverters like Tesla, in which case they basically reflect that the load is covered in the values that when the batteries are operational, there is a standby load that you have to account for. But they are basically saying that you don't have to account for a large amount of load because it's already accounted for. If that's not the case, we do highly encourage specifying 2 to 3%. This is, once again, for that reason we spoke about earlier. It is so much easier to reduce the design of your facility at a later time, reduce the equipment, remove equipment, than it is to add it in. So it could potentially be harder to, specify just a very small amount just so that you can, get the least amount of inverters, and then later on find out that you're going to have to increase that. So we do recommend, as long as it's not causing a huge issue for your initial project design, to go ahead and specify a 2 to 3% if you don't have an exact value. On the other side, we have solar where for the most part you can just estimate a simple amount of station service load. If you had trackers, that might be something to look at on a case-by-case basis on how much aux load that might be if they're getting fed from the AC side. But typically for solar, if it's solar only, you're really just going to specify that small amount of station load, maybe somewhere in the 100 kilowatt range should be sufficient for getting some value in there for load. And the other thing to consider, which we talked about a bit this morning, and as the question was asked, following up on that, I mean, you could end up needing to feed your auxiliary power from the local PTO. And this is something that you might not be able to determine at these very initial steps, but you could certainly get in conversations with the local PTO, with the local distribution owner, and start determining if that's going to be a requirement, or in some cases, I don't think most, I think it's probably cheaper to feed your own load, but in some cases, maybe for your design, you would like to be fed from the local distribution service. And in which case, you would need to start those conversations with the distribution service provider. But we still recommend, if you aren't certain at these beginning stages, to just go ahead and specify that higher auxiliary load amount, and then know that you can remove that later on as needed. So the next kind of component here is the pad mounted GSU transformers. We won't go into too much on this because typically what happens and what you should do is, if you choose a certain inverter, then you're going to want to go with the pad mount transformer that they recommend. Oftentimes, even for the inverter manufacturers, this is just within a range. But certain things like your winding configurations will potentially be determined by your inverter. So for the GSU transformers, unless you have a good reason or you vetted out another transformer option, typically it's just best to go with the what's provided in the datasheet or what's suggested by the inverter manufacturer. For these GSU transformers, typically we're seeing 5.75 to 8.9% impedance, somewhere in the 8 to 12 range for the X over R, and typically a plus minus 2.5%, 2 taps at 2.5% de-energized tap changer. We're not typically seeing the on-load tap changers on these pad mounts. So if you're speccing these pad mounts with the estimates shown before you, that's probably a very reasonable assumption. The next place where we see some folks go wrong is for the MVA capacity. Even though you may be producing less megawatts out of the inverter than the total MVA capacity of the inverter, you always want to specify your pad mount transformers at the MVA capacity, the max MVA capacity of the inverter that you're specifying. This will just avoid headaches down the line. At some point when you're pushing your full reactive power, you could be coming close to the limits on these ratings. And since, I mean, typically the inverter manufacturers are sizing their transformers this way, if you have plans to source your transformers through the inverter manufacturer, this is likely how they're going to be sized. So rule of thumb, if you have a 4 MVA transformer, or if you have a 4 MVA inverter, go ahead and put a 4 MVA pad mount GSU, and that should be fine. on that note, if you do have specifics, definitely work with your consultant as early as possible. It's important to note that any changes in these specifics will impact the megawatt and the MVAR values at the POI in the model. And as some of us may know, if you don't, the megawatt value that is solved for in the power flow model shows up in almost every single document in a interconnection request. So it's not a deal breaker to change things later in the process, but it does require a somewhat of a rework of the entire package when you go through and you change some of these smaller things that may not have a huge impact. So it's just something good to think about if you're trying to cut down of the hours needed to be put into these interconnection request packages. If you have specifics on these things, just let your consultant know in advance. That way that the design that you want can show up in the final model as soon as possible. So the next thing to kind of discuss is the main power transformer. The main power transformer is going to be the main things are going to be how many main power transformers do you want to specify? You can go ahead and specify if you have a 500 megawatt project, go ahead and specify a single main power transformer for that. That is possible. But what we're kind of seeing is that procurement of some of these larger transformers can be a little bit more difficult. The costs can end up being a little bit higher as well. And to some extent, it can be considered a maintenance thing as well. If you need to have only one power transformer down, and if you have three main power transformers that make up all of the capacity for your facility, you could, in theory, have one down and be maintaining and still producing power with the rest of your facility. So that's a potential benefit there as well. One thing to think about and to make sure that your consultant knows as well, if you are going with multiple main power transformers in certain areas, this will alter your modeling approach. ERCOT will not allow you to model your medium voltage bus as being shared for all of your power transformers, which means that even if you have a model that could be done as a single equivalent with 4 main power transformers, you now need to have 4 equivalent models for each of the feeds off of each of the transformers. So not a problem, not even too much extra work, just something to consider about. It will come into play on the dynamic modeling as well. It requires a different power plant controller model, a number of things, but just definitely something to think about. And if you are going to specify more than one, maybe have that discussion with your consultant and see if there are any potential downsides to that. But in most cases, when you hit the 150 to 200 megawatt range, that's when we're typically seeing that you may want to start specifying too, getting a max MPT in the range of 150 to 200. Once again, preference, and if a client, oftentimes I will say this might not apply to all consultants, but if your consultant doesn't deal with the procurement side of things, oftentimes you may actually have a better understanding of what you're ultimately going to procure. So if that is the case, once again, just be vocal, share your input with your consultant, and make sure that they're specifying a design that's as close as possible to the design that you will actually be procuring. If you don't have these values, it is totally fine. And the typical approach is to go 1.2 times the megawatt output of your facility at the POI to get the highest MVA rating of your MPT. So typically that's what's going to be done. And what that allows for is your transformer at that sizing will not be overloaded even at the highest power factor output and under the worst voltage conditions. So that's kind of a tried and true approach, and that will be used to size the transformer if you do not have those values to provide. Similarly to our other slide, or to the slide on the pad mounts, percent impedance in X over R, typically for these bigger transformers, somewhere in the 8 to 10, maybe 12% range for percent impedance, and X over R probably in the 40 to 60 range. So we have kind of set values that are going to be good estimates. So if you don't know those, then just work with your consultant and have them specify something that's in the ballpark. And to hit this point one more time, if you are unsure, you can go with a higher percent impedance. to see those higher losses and potentially need to overbuild your facility a little bit more so that in the future you could potentially end up with a lower percent impedance and be reducing the overall design rather than adding to it. So just something to think about. If you happen to have the factory acceptance test reports, the FATs as they're called, for a transformer that you know you want to use or that you're going to procure, certainly provide that. I don't think we've actually ever seen a transformer FAT provided at the interconnection stage, but if you had it, certainly provide it, and that will definitely aid in the process with getting the design as close as possible to what will actually be built. I'm realizing that I left out the collector system. There's not a whole lot to talk about the collector system that wasn't covered in the discussion on the detailed site plan and the sizing. If you have a detailed site plan, you're going to determine your collector system off of that. If you don't have a collector system off of that, just make sure you're working with your consultant to see that they're, estimating lengths of potential runs of your collector system that are realistic, because you typically shouldn't see more than 2% losses in your collector system. But you're probably not going to see too much less than 1%, or maybe 0.5%. So just kind of, if you aren't sure what's being done, just make sure that your consultant is aware of kind of checking those losses and keeping it in a realistic range of maybe 0.5% to 2%, and you'll be good there. But in these preliminary stages, not too much else to say about that, unless you happen to have such a detailed design that you had the medium voltage cable schedule, in which case certainly share that with your consultant and have them prepare your equivalent collector impedances based on the medium voltage cable schedule. So going with the gen tie, similar to what I touched on a little bit earlier, the gen tie is, it ultimately comes down to just a handful of impedances that get plugged into the model. But if you are sitting there changing your gen tie length and route and all these things consistently throughout the process, while your consultant is trying to pin down these megawatt values and MVAR values at the POI, or megawatt values at the POI, this can just cause a lot of rework to have to be done. So we recommend having your gen tie vetted out as much as possible before you even give the information to your consultant to have them start on the project. A consultant will be very happy if they don't have to go back and rework the design for increasing the impedance or decreasing the impedance on a gen tie. We understand that's not always possible, but we just do want to recommend that within reason, if you can manage to maintain your gen tie route for the length of the interconnection request, the initial submission, that will definitely save some time there on getting these things turned around. So things to consider when you're going to be giving your design for your gen tie. One thing that we don't see come into play always, but that should be considered, is do you think there's a possibility that you're going to have another phase, you're going to submit for an additional amount of megawatts in a different project that will share the same gen tie? You obviously don't want to unnecessarily oversize your conductor. It's a higher cost for a larger conductor. You'll see less losses on that as well. So if you oversize it too much and then you end up reducing it, once again, that goes back to the overbuilding versus underbuilding. There could potentially be some issues there. Not too many though. So if you have the thought that there's potential for your project to have an expansion that is pretty reasonable, definitely go ahead and consider sharing that information with your consultant and saying, hey, we have 100 megawatts for this cluster right now, but we might be submitting another 100 in the next cluster. So can you size this gen tie for 200 megawatts? And that's an easy enough thing to do, and good to get it into the design in the beginning. If it does need to get changed down the line, not a huge deal at all. So definitely something to consider. The next thing, we touched on this a bit this morning as well, is considering your right-of-ways when you're looking at your gen tie route. It is going to be difficult in these early stages to know everything about those right-of-ways and what's what's likely to be able to be obtained and what's not, based on not knowing who the landowners are and all sorts of things. So really what you can do best is just try and have your gen-tie route be as short as possible. And when you're looking for the route that you want to take, try to cross over as few different pieces of land as possible, because it will cut down on the number of different folks you have to work with for right-of-ways. I myself am not an expert in this side of things. I don't really deal with obtaining the land and things like that. But I do know that that is something that you can look out for. So, oh yeah, I touched on this already. So changing the gen-tie length definitely can be done. You don't have to have the final gen-tie length before the package is started, but anything that you can do to have that pinned down ahead of time is definitely much appreciated by your consultant. Okay, so this is a topic that I did want to throw in here. We will be having a discussion, I believe it is tomorrow. Pat will be giving a discussion on metering. I myself am not a metering expert. Casey is he's the guy as well. So I did just want to at least include in here that this is something that you should be thinking about at this point in time, but it's not going to typically show up in your interconnection request package. But that doesn't mean that you shouldn't be considering it and that you shouldn't be maybe talking to an expert about it in these beginning stages just to prepare yourself. As we kind of touched on before, there's a lot of things like the charging sources for your storage. Are you going to have phasing? Are you going to be co-located versus hybrid? And another thing to consider is how many off-takers you'll have for the project. So there's just a number of things that you can that could come into play with this metering design. And the E&I group itself is actually at any particular spot might not be the best to talk about this, but definitely go out and find yourself a metering expert and talk to them about, the potential roadblocks you could run into. Okay, so this is an area that, you typically, your consultant's going to be dealing with the majority of the work on the modeling side, but we kind of touched on a bit of this earlier. There is a number of areas where the different inputs from teams can overlap. And just to save on time with preparing these packages and ultimately to save on deficiencies, because the back and forth can often lead to items that don't get updated and changes that just didn't get quite made correctly. So it's always best when possible to have the initial design and stay with it. So kind of our first recommendation is, pick your inverter at the beginning and just stick with it. If you get 50% of the way through the interconnection request, you have a pretty good package pulled together, you're getting ready to submit it. Unless you have a really, really good reason that you need to change the inverters, for the sake of time, it's definitely best to just go ahead and stick with that inverter. You can file an MMA at a later time, and you can you can change that later on down the line. And you're most likely going to have to anyways, because the inverter you select likely won't be procurable by the time that you go to construct your facility. So we do recommend that you pick your inverter at the beginning and stick with it. If you have really good reasoning to change, it does just need to be known that that really changes the whole entire interconnection request package, down to the dynamic model and everything like that, the inverter count, collector system equivalent. So if you are on a time crunch, we highly recommend going with what you select in the beginning and sticking with it. The other thing to think about for these modeling purposes is what inverter manufacturer will support the models that you need to submit. For most inverter manufacturers these days, it is not a problem to get your PSLF and your PSSE models. Certainly not a big deal. But what we have seen is that some inverter manufacturers don't have readily available info for Aspen, for PSCAD, or they're just harder to work with for some of these more specifics. So, I mean, to be honest, even if you really like an inverter manufacturer, and you think it fits your project well, if you know going into an interconnection request process that there is a requirement that your inverter manufacturer can't fulfill, as much as you might like to go with them, you just know that that's going to be a roadblock that could result in your project not making it through the process. So for these initial stages, while we do recommend getting as close as possible to your final design, if you really don't know much about which inverter you're going to select, we highly recommend working with your consultant and saying, hey, who has the most complete technical data package and is the least likely for me to end up with deficiencies based on the info that I'm able to provide. Because sometimes it could be even hard to get a reactive capability curve from someone for a certain temperature range or a number of different things. The short circuit data is often requested by utilities in a number of different formats. So while they might have the short circuit data for your basic current values, they might not have the NERC table, which is provided by or required by some folks like KISO. So if you aren't sure about your inverter, then work with your consultant to figure out what inverters have really nice technical data packages. And if you are sure about your inverter, then go ahead and make sure you're working with your manufacturer contact to make sure that you have all the data that you need up front ahead of getting into the interconnection request package, and definitely ahead of providing that information to your or the inverter selection to your consultant. Another thing, I guess we'll just touch on it again. We talked about it in good detail above, but the detailed site plan and the power flow, definitely going to be some amount of iteration involved there if you do have to submit that detailed site plan. So as I mentioned before, communication with your consultant and the team who is preparing the detailed site plan, potentially the same people. If that's the case, that's fantastic. If it's not, it's certainly not a problem, but just making sure that there's good communication on any design changes or any specific needs that have to be met in one side, the power flow versus the detailed site plan, or the detailed site plan versus the power flow, because that could result in some really messy deficiencies that there is no way around other than we're completely reworking one of those items, and those make up pretty big items as far as the interconnection request package is concerned. I guess I mentioned this a couple of times already, but determine that realistic gen tie. It's definitely going to help you, going to save you some time, and the less you have to change on that, the less you'll have to change across the package. Okay, so we wanted to provide a little bit of PSCAD EMT specifics. I will be honest and say that I am not a PSCAD expert myself. I don't work in it very much at all, but I did have some very nice engineers here pull this together for me. So this will be a little bit more of reading off some info and letting you know some stuff. But at a high level with the PSCAD, the kind of the issues that we're seeing is when it is being required, the utilities are pretty typically using it. Well, we seem to feel that the utilities often use this as an additional way to weed out potential interconnection clients. We have submitted a lot of PSCAD models to utilities, and we very rarely receive deficiencies on these. And we would like to think we're perfect, but we know that we have received our fair share of deficiencies and our fair share of learning experiences throughout our time with dealing with the interconnection request process. And it's very unlikely that these models are truly deficiency free as they're submitted. Even it comes down to just very, very minor things. A 0 where a 1 is supposed to be. So the fact that we haven't seen a lot of these be reviewed, we do feel that it is more of a check this box, we'll use it later, maybe sort of thing. So consider this when you are building your interconnection request package. But what we can say is that now that more utilities are requiring it, we have started to see more deficiencies come through. So we're kind of in this turning point right now, where it's really unclear how these models are exactly going to be used. Are they being requested in the very beginning to weed folks out, or are they actually going to start studies in the beginning? Most of the time, it seems to be they're using these later on down the line. So if that's the case, just understand this and work with your consultant, because I can tell you from the experience I have had working with folks on these mod test level PSCAD models, on these constructed facility PSCAD models, they can be a lot of work and there are a lot of specifics. And when you have to get on calls with the OEM to kind of work through a lot of these issues, it ends up being a lot of work and a lot of time invested, and these are very detailed models to pull together. So kind of know the requirements for the utility, work with your consultant to see what they might think. If you think you can just go ahead and submit the model, get that box checked, that's great. But definitely, if you have a pretty good feeling that this is going to get scrutinized very well, then going back to our point above, you really, really want to make sure that you're working with an OEM who can support you, because they know these models very, very well. And oftentimes, no matter how long an engineer has been doing PSCAD, the OEMs just know their models in and out, and you might not be able to get away without working with them. It's just a little bit of warning with the PSCAD that it might start to show up as a bit more work, and you might want to be contemplating this PSCAD model development earlier in the process. Yep. So procurable equipment, as I mentioned before, here at GridSME, we don't deal with the procuring of equipment for clients or any of that side. So I think for some of you folks out there, you may actually have a really good handle on this procurable equipment, potentially more than your consultant who is the interconnection expert. So if that's the case, definitely, once again, make sure you're sharing this information. And if you have reasons to select a certain piece of equipment or specify a certain aspect of the design that your consultant hasn't brought up, definitely talk about it, because the procurable equipment could it is getting to a point where it is affecting the interconnection timelines. We talked about it a bit this morning about circuit breaker procurements, particularly. There's a lot of long lead items now, and if you are somebody who has these has a feeler out for these because you're out there constructing projects and you're in the life range of projects from start to finish, then you might have some really valuable information on what are some realistic pieces of equipment to specify for a project. So in that case, definitely be considering that when you can, and take into account that your procurable equipment could slow down your ability to interconnect your project seamlessly. Particularly what we notice is, on these fast track, these Rule 21, net energy metering, behind the meter, these projects that move a lot faster, even though they're smaller projects and it is a smaller amount of equipment to procure, you really have to have your design vetted out up front as much as possible. So even more so in those cases, definitely make sure that you have vetted out the best possible equipment for your project. All right, so this is a slide that I wanted to throw in here towards the end. We here at GridSME do not do a whole lot with PPAs. We're not very heavily involved with them, but I did feel it was important to note this as something. Maybe it actually should have gone with this morning's presentation now that I think about it, but it's an important thing to note nonetheless. As we look at viability of projects and their possibility to survive in this new landscape of interconnection requests, PPAs are going to be an important part of that. And so it's definitely something to start considering and start looking into as early as possible in the life cycle of your project. If your interconnection consultant is not the expert in PPAs, maybe go out there and find somebody who is an expert in PPAs and get that discussion started and figure out how you might be able to get a PPA and where those are coming from. And if that's going to be something that is even feasible for your project, where you plan to interconnect it, because that a project could make it all the way and then fall short on this one item. And so even though it is just one item, it is still enough to stop a project in its tracks. And we do feel that it's important to make sure that PPAs and sorting that out is something that is being factored into your project as early as possible in the life cycle. So kind of closing up on the big picture from this morning's presentation and this presentation now, I think the big word of advice is that it's going to be important to invest a little bit more in your project upfront as compared to how things were in the past. Don't think of it as throwing money away. Think of it as putting a little bit more into making sure that your project is viable. We just see a lot of the times that folks are trying to scrimp and save on their project as much as they can in the beginning, so that they can wait until they find out if it's viable or not. The harsh truth is that here in this new kind of approach to everything is that you really need to make sure your project is viable up front. So you could be saving yourself a lot in the long run if you just invest in those additional things, those detailed site plans, those potentially capacity analysis, items like that. Those could really pay off for your project in the long run. So just start considering that more and do whatever you can to make sure that your project is viable as soon as possible. And I think I saw a question come in already.
No, that was me providing more information on IEEE 2800. So,
Cool.
but with all that said, I am going to go ahead and unmute everybody. So you have the option to unmute yourself if you have a question. So feel free to just jump in and ask your question, or if you prefer to type your question in the chat, by all means do that as well. So we're open for questions now.